Okay, now let's take a look at our lemma 3 and lemma 4 again. And I know that you may wonder why we introduced the spaces U1 through US. And in particular, what role will U1 through US play in our proof of Kronecker's theorem? How is the basis associated to this defining approximation in the inhomogeneous setting? And now, let me answer this question with a corollary to the lemma 4. So, corollary to lemma 4. This corollary states that it suffices to prove Kronecker's theorem, the direction from 2 to 1 for all B in Rm with Ui transpose times B equal to 0 for any I greater or equal to 1 less than or equal to S, where those U sub i's, as before, are a basis of the abelian group script M. So this corollary tells you to prove the Kronecker's theorem, the direction 2 to 1, you don't have to consider all those vector b's. You only have to consider those b's which have some special interaction with those basis vectors U sub i's. And that somewhat simplifies this proof. So now let's prove this. Let vector B in Rm be any vector satisfying the statement number 2 in Kronecker's theorem, namely, whenever you have a Tu is in Zn and U is in Zm, you will have UTB is an integer. And assume for this B, we have that Ui transpose times B is equal to Wi for any I greater or equal to 1 less than or equal to S. And now, by lemma 4, here's our lemma 4. We're able to find a vector in lambda such that, so by lemma 4, there exists a Z written as AQ minus P in lambda, where P is in Zm, Q is in Zn, such that UIT times Z is equal to negative omega I, which is in Z, for any I greater or equal to 1 less than or equal to S. Actually, it doesn't matter if you put the plus sign in here. We use the minus sign so that the format of the defining approximation will coincide with the statement of the Kronecker's theorem. And it follows that UI transpose times AQ minus P plus B is equal to 0 for any I greater than equal to 1 less than or equal to S. And now you see, because this follows from adding up those two equations. That is why we choose negative sign here, so that we get the plus sign here. Otherwise, we get a negative sign, but it doesn't matter. And now I believe you know what we are doing now. What we are doing is that we start with an arbitrary b, any vector that satisfies this second statement of the Kronecker's theorem. And we produced another vector that satisfies this hypothesis, this additional hypothesis. So let us call this part B prime. And we are going to verify that this B prime also satisfies the original hypothesis. So let's check this. If A transpose times U is in Zn and U is in Zm, then U transpose B prime, which is equal to U transpose AQ minus P plus U transpose times B. We want to see whether this guy will also be an integer. You already know this part is an integer. This is because the first part is UTA times Q minus UTP, and UTA, which is a transpose of this, is an integer row vector. So this part is in ZNT. Therefore, because P and Q are both integer valued, this whole thing is an integer. And this is an integer by our assumption above. So this whole thing is an integer. Therefore, B prime satisfies all of our hypotheses for this corollary to lemma 4. And now, because we assumed that the Kronecker's theorem is already proved for this special B, which is B prime in our case, with this additional hypothesis, we have for this B prime, so Kronecker's theorem 2 to 1 is proved for this B prime equal to AQ minus P plus B, which means for any epsilon greater than 0, there exists P prime in Zm and Q prime in Zn, such that aq prime minus p prime plus b prime has the maximum norm less than epsilon. And if you plug in the expression for b prime in here, you will get the maximum norm of a times q prime plus q minus p prime plus p plus b is less than epsilon, which proves the Kronecker theorem for the vector b. This b is an arbitrary one, satisfying this hypothesis with p prime plus p in Zm and q prime plus q in Zn. And that finishes the proof of this corollary.